All right, greetings, guys. We're going to talk about something called infinite geometric series. Sometimes in mathematics, the concept is the hard part to wrap your mind around, but the actual number crunching is easy. Please watch the entire video so you are familiar with the underlying concept. Thanks. Let's begin. This is called infinite geometric series. So just to start off with, there is no such thing as an infinite arithmetic series. If you look on Canvas, you see how I have the unit broken down into components. This is the last lesson. There is no such thing as an infinite arithmetic series, so this is where we put the brakes on. Now, the concept's going to be weird. So give it time. You got to kind of pay attention to what's going on. But when you do finally get to the end of the road, you're going to see that the actual number crunching really is easy. But I wanted to start out with this guy right here, because this one right here is easy to see the pattern develop. So let's begin. This is a series. Remember, whenever you see the sigma symbol, whenever you see... Whoop. Gotta get my pen working here. Whenever you see this, dude, you know it's series, not sequence. So it means I'm going to be adding things. Also, whenever you see it written like a numerical value to a power, whenever you see that, you know that it's geometric. And when you see this guy, which we have not seen before, at the top of our sigma, then you know it's infinite. Now, your brain might say, well, I know what a series is. It's when you punch in the numbers and you add it up, but usually they tell me to stop. They say, like, stop after the first 5 or 7 or whatever. What does it mean if it goes forever? Well, your brain says, if I keep plugging numbers in, like this one, if I plug a 1 in, I get out 1/2. If I plug a 2 in, I'd get 1/2 squared. Well, what's 1/2 squared? It's 1/4. And if I plug in 3, I'd get 1/2 times 1/2 times 1/2. I'd get 1/8. And hey, guess what? Since it is geometric, I know, I'm going to get this out of my way, I know that this is my R value, because that's the way it's written. So I could just multiply by 1/2 and say, oh, well, the next one's 1/16. Multiply by 1/2, the next one is 1/32. Multiply by 1/2, the next one's 1/64. I could keep doing this, but what's going to happen is I'm going to run out of room, so I'm just going to stop right there. And away we go. Now, you might say to yourself, well, I keep adding numbers, it just must get infinitely big. And the answer is no. Your brain wants that to happen, but it actually does not. This right here, this guy, this dude that I made up, this exact problem right here is a fancy way to say 1. The answer is 1. What? Pay attention. I'm going to go through a couple of these so you see this pattern develop. But I want you to know, you do not have to write it out in this huge, long string of stuff to understand that the answer to this one is 1. There is a beautiful, tiny little shortcut I'm going to show you. But I want to make sure you get the concept. So let's begin. If I were to just add the first 2 numbers, if I said, well, what's 1/2 plus 1/4? Well, that would be 3/4. And you can check me on your calculator for any of this. And then I'd say, well, what's 3/4 plus 1/8? What if I added the next number to the puzzle? Well, 3/4 same as 6/8, so plus 1/8, I'd be at 7/8 here. And then what if I was to add 1/16 to that? What if I added up all the way to 1/16? Well, this is just the same thing as 14/16, so I add one more, I'd get 15/16. Now, the pattern, as I keep going, well, I add 1/32, I will get 31/32. If I add this, I'll get 63/64. As I keep going, what's happening is my answers are getting closer and closer and closer to some number that lives on our number line. And remember, if I kept doing this forever, it's going to smack into this number on the number line. That's the limiting value. Now, let's wrap our minds around this. In graphing, when there's a boundary marker, we call it an asymptote. So an asymptote is a graphing concept where there's a boundary marker. Well, this, when it's numeric, we call it a point of convergence. Now, in calculus, you will hear the words converge, and you will hear the words diverge a lot. So anything that converges will reach a value that we all agree on. If I keep doing this forever and ever and ever and ever and ever and ever and infinitely, what you're going to see is, one seems to be where it's headed. One's the guy. That's called the infinite sum of this geometric series. Now, not every geometric series adds up to 1. I've made up a couple examples so I can show you. But I'm not going to be doing this the long way for long. Take a look at this one. What I am hoping is that you have in your brain case the vibe that, hey, yeah, this is what geometric things look like. And if I plug in 1 this time, I would get 3 times 1/4 to the 0. Well, anything to the power 0 is 1, so it'd be just 3 times 1. I'd get out 3. And then if I were to plug in 2 for n, if I were to plug a 2 in here, I'd get 1/4 to the 1st times 3. I'd get 3/4 out. And if I were to plug in 3, I would get a barking dog next door, and 3 minus 1 is 2. I'd get 1/4 squared, that's 1/16 times 3. But you know what I'm trying to say is, we all know that once we see it, we see this pattern develop here. And I don't really have to go much farther because I'm running out of room on my screen. But let's do this. I'm going to grab my calculator and say, well, you know what? Let's experiment. 3 plus 3/4 would be 3 3/4. That's what it would be. Now, I'm going to take 3 3/4, and I am going to add to that 3/16. Okay, now just so you know, my calculator is going to keep spitting out decimals for me, and I don't have time to math frac and convert and everything, so let's just play it this way. This first total would be 3.75, but if I add in the next number, the total on my calculator screen is this, 3.9375. But I'm going to add 3/64 to that. So I'm going to say on my calculator, let's add 3/64, and what do I get? Well, this next number, and then they're starting to get bigger, so I'm going to write it here. I'm going to go, that would be 3.984375. I'm going to add one more. I'll go 3 over 256. So let's add that in. We'll go plus 3 256. And now my answer, just going out, 1, 2, 3, 4, 5 answers. This answer is 3.99609. Yeah. What number do you think this thing is trying to get close to? What numerical value on the number line do you think this is going to converge to? Well, the answer is 4. This is a real fancy way to say 4. So the thing is you could keep going. You could, hey, I could do another one I could say, you know, the next one in the list here would be 3 over 1024. I could add that in to my last answer. And I could see that this thing is just going to get closer. And it's going to get closer and closer to 4 the farther I go out. But I'm trying to tell you, there is a shortcut way to come up with the answer. So you never ever will have to write an expansion out forever and ever and ever to see this occur. I'll show you a shortcut. But I want you to wrap your mind around the fact that these are what we call infinite geometric series. And they don't always write it with sigma. Sometimes the original problem is expressed like this. They'll say something like, find the infinite sum given the following. So when you guys get to the practice problems, some of them are written in sigma notation, and some of them just look like this. Find the infinite sum. Now, I want to write in one little tiny thing here because this is important. Usually, and I'm going to change colors so you see it, the work that we've done so far, it'll say like to 10 terms, you know, or it'll say to 8 terms. If they give me a concrete stopping point, if they give me a location where I am going to have to put on the brakes, then I cannot use the infinite geometric series formula. What? There's a formula? Yes, there is. But if they want me to actually stop somewhere, I have to use this guy where I'm doing this thing. That is the formula that I get to use if it's finite. But since this says find the infinite sum, since they say find the infinite sum, I don't use this formula. I got a different formula. Let me get rid of this stuff. I want to erase it now. I want to get it out of my face. So I'm going to erase all this junk. Because the original problem did not tell me to stop. So you don't want to do it the old-fashioned way. You don't want to go, okay, 5 plus 1, that's 6. And then I get 6 plus 1/5. Well, that's 6 and 1/5. Or what my calculator would say, 6.2. And then I'm grabbing my calculator one more time. 6.2 plus 1/25. Oh, well, that's 6.24. Now, just for kicks, I'm going to do this one more time. The next number in my list would be that. So I'd say I'm going to add that, and I go plus 1/125. And then I get this. I get 6.248. Etc., etc. I could keep going. What the heck? One more time. One more time. So if I added that to the puzzle, I'd get 6.2496. What number do you think this is getting closer to, guys? The number this thing would be getting closer to is 6 1/4. That's the number it's getting closer to. 6 1/4. That is where this infinite geometric series will converge. That will be the solution, the answer that they're looking for. Now, let's tell you something. Okay. Okay, wait a minute. Sorry, that was not what I wanted to do. Oh, that's why I left myself some space here. Sorry. So here we go. There is a formula for an infinite geometric series. It's this. That's it. If you know what the A1 value is, if you know where the list starts, hey, there it is, it's A1. And you know what R is, well, hey, take any number in the list, divide by the one that came before it. Take any number in the list, divide by 1/5. That's R. Oh, if you know what A1 is and you know what R is, guess what? You plug it into this thing and you go A1 over 1 minus R. 1 take away 1/5. Well, that's 4/5. So what does this thing become? It becomes 5 divided by 4/5. Well, wait a minute. That just means flip. I could actually punch this into my calculator right now. It's going to give me this, 25/4. And then I go, wait a minute. That's an improper number. Improper answers are not wrong. They're fine. But if you did convert it, guess what? You get 6 1/4. That's what you'd get. See, this is the formula. The concept is weird, but the actual formula you have to use is extremely tiny. It's a baby formula. It really is. Now, let me go back. I just want to prove to you that this formula works. I don't have to ever write out a long string of stuff to get my answers. I don't. Could I? Yes. But why would I do that if I know there's a really easy way to get there? So here we go. I wanted to come back to this one. What's the A1 in this problem? Let's use a different color. The A1 value is 3. That guy's R. And I go, oh, okay, so the formula is A1 divided by 1 minus R. What does that equal? Well, that equals 3 divided by, well, 1 take away 1/4 is 3/4. And that looks, oh, that's a double fraction. Well, you can do this one pretty easy because it's just 3 divided by 3/4. That's all it means. Which means I could flip and multiply. And if I did, guess what? Bam! There's my answer. I don't have to write it out in a big long string. As long as I know A1 and R, I'm good. Let's go back to my first example. Right? This guy, the big difference was somebody wrote this one impolitely. Remember, most of us, we go, oh, n minus 1 is the correct polite way to write things. But if they didn't write it politely, it doesn't mean you can't do it. Just because they were impolite, you could still plug in 1 and find out that that's A1. You can still say that thing is R. It's still R. It hasn't changed. So let's use the formula. What did the formula say? It says, let me get it, the infinite sum is equal to A1 divided by 1 minus R. Well, what's A1 in this problem? 1/2. What's R in this problem? 1/2. So 1/2 divided by, well, 1 take away 1/2, it's 1/2. Oh, that one's easy. I can do that in my head. Anything divided by itself must be, what? 1. Bam. There's my answer. It equals 1. Boom. The actual number crunching is easy. It's the concept that's really weird here. So before I do anything else, just let me remind you, sometimes in mathematics, the concept is the hard part to wrap your mind around, but the actual number crunching is easy. And I'm going to say, please watch the entire video because I got more stuff to tell you because I left one little thing out. So now I'm going to scroll down to the part that I left out. Okay, not that part. We did that part. That's when I wrote the formula. But the thing is, see this formula here? It's incomplete. There's one piece of the puzzle I left out. It's true. Let me show you. And that's what this part. Okay, the instructions will also state, find the infinite sum if it exists. So I know what you're saying. You're like, what does this mean? What does that mean? Well, here are examples of infinite sums that don't exist. These do not exist. What does that mean? Hold on, I'm going to get you there, I promise. Let me get my black pen back. Okay. This one, the first one I made up, is really obvious. 3 plus 6 plus 12 plus, what do you think the next number is in this list? Well, 24 plus 48 plus, well, here's the thing with this. This thing, in math, we say this diverges, meaning it does not approach a single value that we all agree upon. And you might say, sure, it just gets big forever and ever. It becomes infinitely large. And I say unto you, show me on a number line where infinity is. That's a hobby that lasts forever, because you can never find infinity on a number line because it's not a number. It's a concept. When you guys get to calculus, you would find that the answer in the back would say this diverges to infinity. That's what it would say, diverges to infinity. Meaning there is no single number answer this is going to approach. But here is the reason. I left this out of the formula, so I'm going to show it to you now. Here's the part of the formula I need you to see. Where did I write it? Ba-boom. First off, just a reminder, there is no such thing as an infinite arithmetic series. They will all either get infinitely big or infinitely tiny. But the formula for the infinite geometric series is this, and here's the part I left out, where r, absolute value of r, is less than 1. That's the part of the formula I left out. See, here's the phenomenon. Here's how it works. Think of numbers that's absolute value is less than 1. Let me just give you a couple examples. With 3/5, if I took its absolute value, would it be less than 1? You'd say, sure. What about -3/5? Sure, that would work too. But if I said, what about the absolute value of 2? Is that less than 1? Nope. God, that's a horrible N. There we go. Nope, it's not. So the thing is, there is a restriction on this. That's a restriction. The only time this phenomenon occurs where you can keep adding and adding and adding and it never gets bigger than a certain number is only when the R value is, well, this is a fancy way to say this. These are equivalent statements in mathematics. This is more compact, so the book uses this. But any number that is between -1 and 1, which means proper fractions. If it's a proper fraction, it's valid. Most people go, what do you mean? Because I've heard the word improper fraction. Yeah, but guess what? If you're not improper, you're proper. So anything like 1/2, that fits the category. 1/4, that's totally fine. What about 3/5, -3/5? Yes, all this stuff works. Any proper fraction, and you can find a limiting value to your answer. But these guys, let's go back. These guys right here, the sum does not exist. This would just get infinitely large, this first one. So this guy is not an infinite sum that exists. This one right here is kind of sneaky. I was trying to be sneaky on the second one because it goes back and forth, back and forth, back and forth. But take any number in the list, divide by the one that came before it. -5 divided by 4. What do you notice about that number? Take its absolute value. That absolute value would be 5/4, or we could say 1 1/4, and that is definitely bigger than 1, so it does not count. This guy right here, you could try, but you will not get an answer. Okay. Look at this one. This one right here, this example, sometimes they'll write the original problem so it has sigma notation and it'll do this. But if you know what you're looking at, what is the R value here? What is the R value here? Well, the R value is 7/3. And once again, you take the absolute value of 7/3 and you will get 2 1/3. And that is definitely not less than 1. That is not true. So if it's not true, if it's not less than 1, you say the infinite sum does not exist. That's what you say. So be very careful. They'll be sneaky in the assignment. They'll give you ones that work and ones that don't work right next to each other, and you've got to decide which are which. But it's not hard to figure out. Just remember, it's got to be a proper fraction, and you'll be okay. R must be a proper fraction for it to work. Now, here is the thing. I love this part of the lesson because you guys know this already. Repeating decimals are infinite geometric series in disguise. Repeating decimals are infinite geometric series in disguise. And this one right here is not decimals. It's not written in decimal form. It's not. But I want to kind of piece this together so you see this. Remember, the concept can be difficult. The number crunching is going to be easy. But here we go. Do you guys agree with me that this is A1? Do you guys agree with me that they want me to go add this list of numbers up forever? Yes. Take any number in the list, divide by the one that came before it. And if I was to do that, I would flip and multiply. So this thing becomes what? It would be 3/100ths times 10 over 3. I can cross cancel. So I get 1/10. And I go, ooh, that's R. And then you go, hey, R happens to be a proper fraction. Proper. So I am going to plug this in. I'm going to plug this thing into my formula. This formula right here. And I noticed when I notice things when I say them. If you write a formula out every time you have to use it, eventually it gets burned into your memory. It's like mental flashcarding. So here we go. I'm going to use this formula, and I'm going to say A1 over 1 minus R and 1 minus 1/10. What is 1 minus 1/10? It's 9/10. It's 9/10. So, let me think here. So 3/10 divided by 9/10. We're going to do 3/10 times 10/9. Ka-ching, ka-ching. Hey, I could do this too. What the heck? Oh, the answer is 1/3. So this right here, the sum of this forever would be 1/3. Now, I know for a fact that 1/3 is my buddy 0.3 repeating. My friend 1/3 here is equal to this. And you guys know that for a fact. Okay? I can say, hey, do you know that 1/3 is the same as 0.3 repeating? And you go, yeah, totally. Everybody knows that. But the thing is, if I say why is the reverse true? Why is 0.3 repeating the same as 1/3? Well, here's why. Look at my original problem. I wrote it like this. 3/10 plus 3/100ths plus 3/1000ths plus 3/10,000ths plus ... I went on forever, right? That's how I wrote the original question. But guess what? That's the same as 0.3. That's 3/10. Plus, that's 3/100. Plus, that's 3/1000. Plus, and you go, wait a minute, there's a pattern. Yes, indeedly. Oh my God, that sounds like Ned Flanders. Anyway, well, you go, okay, well, what does that mean? Well, take a look. I'm going to write it this way. Check this out. This is where math gets beautiful in my book. I could write it like this if I wanted to. Remember when they taught you how to add decimals, they told you to line up the decimal points? Well, that's all I'm doing. But I could do this forever. Oh my gosh, I could make this last forever. I could do this. And if I did, what would happen? Add straight down. What would happen? You would get a pattern of 0.3333333. If it goes on forever, they taught us in the 4th grade, stick a bar over it. There you go. So what I'm trying to say is, when you guys see a repeating decimal, you can always break it down into this style pattern. You could. And if you could do that, I could convert it into fraction form if I wanted to. I don't have to. But, hey, I didn't do anything slick or tricky here. There's A1, 3/10. I found out what R is. It's 1/10. I plugged it into this formula, and I got 1/3. Every repeating decimal that you know is an infinite geometric series in disguise. So in the book, they are going to do something like this to you. They are, not going to lie. And they're just going to go bling, bling, bling. And they're going to say, find the sum if it exists. And I go, okay, take any number in the list, divide by the one that came before it. See, I didn't write this one in fraction form. I didn't. But if I did this, I don't know about you guys. I could punch this in on my calculator. I'm going to get 0.1. I fully will get 0.1. I will. Take any number in the list. I don't believe you. Take any number in the list. Divide by the one that came before it. Punch it in on your... You know what? I'm just going to grab my calc, just so you can hear the click of the keys. It's 0.1. Sure it is. So if I do that, that thing that I just found, what is its name? It's R. Do you guys see that this is A1? Because that's the first number they wrote in the list. It is. Now, 0.4 plus 0.04 plus 0.004. Guess what? That thing is the same as, just like I showed you before. Just like I just showed you. I could do this forever. What's the result going to be? 0.444444444. So this is 0.4 repeating. But you know what? It's got a actual fraction representation that I know is based on this. It's based on this. 0.4 divided by 1 minus 0.1. Well, 1 take away 0.1 is the same as 0.9. And then back in the 4th grade, they showed me this trick. If you move the top decimal, you move the bottom one equivalently. And then you go, oh, that's just 4/9. Bam. That's the answer. 0.4 repeating is the same thing as 4/9. It is. Do all repeating decimals follow this pattern? I use the word pattern, and it is a pattern. So let's just take a look, because here's what it says in the book. It'll say something like this: 0.32, bar over it, right? Convert this to a fraction. Well, how do I do it? Well, there's 2 digits repeating this time, so if I were to write it out, I like to write it this way, because I know there'd have to be 2 zeros here and then 3 2. And if I was going to write out the next one, I'd need 4 zeros. And I'm just going to do this one more time because it's annoying. If I did this forever and never stopped, When I add straight down, guess what would happen? I'd get 0.32, 32, 32, 32. It would keep going forever, which is what an infinite repeating decimal does. That's what they do. But take any number in this list. How about this guy? Take any number in the list. Divide by the one that came before it. If you get the same answer every time, you know it's geometric because that is called a common ratio. I will leave it up to you to verify this, but every single time you do this, you're going to get 0.01. And that's going to be called R. This is the first number I wrote down. I'm going to call it A1. And I am going to use this formula, otra vez, 0.32 divided by 1 minus 0.01, which gives me 0.32 over 0.99, and then kabam, kabizzle, I'm going to move it. I like to move it, and I get 32/99. Bam-a-witch. How cool is that? The only thing I ever have to worry about when I do this is, does this answer that I get at the end, does it reduce? Sometimes it does, sometimes it doesn't. If it reduces, that's coolio. If it don't, it don't. And this one doesn't, so I'm just going to stop. That's good. So when you guys see these problems on the homework, when you see the ones that go like this, 0.643 repeating, they could either write it like this, that could be the way they present it, or they could say something like this. Right? Guess what? That's this. Well, how do you visualize it? Please visualize it like this. Do that forever. And then what would happen? You would generate this pattern. And then you say, hey, I'm going to call you A1. I'm going to take any number in my list, divide by the one that came before it. I'm going to get an answer, right? Point, and then, guess what? Bam, there it is. And then all I have to do is plug that stuff into the formula because I already have A1 and I already have R. Yow, there it is. So, here's the dealio, yo. Oh, and do you notice? That's definitely a number that is between -1 and 1. It fully is. So was this. This was a number right here between -1 and 1. Oh, yeah, yeah, yeah. También esto. All right. So the thing is, I'm going to just tell you. Let's look at the assignment. Here we go. We're going all the way up. Yeah. Hey, this came out of your math book. I don't hate the Big Ideas Algebra 2 math book. I don't. It's a great book. The thing is, I had to condense all your information into something I could do in 12 weeks. So I just took stuff and put it onto, all in one spot, guys. But you know what? This is, just in case you were wondering, yes, here's what your math book looks like inside. I don't want you to do number 25, not on your test. We'll stop at 24, okay? 7 to 24 all, so you're not doing these. So look at the instructions, and if you're like, I can't read that, guess what? You have a book. You do. You could open the book to page 439, 7 to 24 all, and they're all right there. Now, it says, in exercise 7 through 14, find the sum of the infinite geometric series if it exists. So on some of those, how do you know if it exists? The R value. You got to key in on that first. Don't just start trying to work on it. Notice about the R value before you do anything. And that's what 15 and 16 are about. Take a look at number 15 and 16. Now, here's the thing. I want you guys to try out these two word problems. And here's the thing. You might get it right off the bat, or you might not. How do I know if I got it right? Well, there's an answer key. There it is. But anyway, hang on. The thing is, this is where people start getting stuck on this. And usually when you get stuck, it means you need to come into the Zoom room and ask for help. Some of you guys have not done that. So do it. Please do it. Because coming into the Zoom room, I can actually one-on-one help you out. But I'm going to leave this up to you and see if you figure it out. And of course, you might get the wrong answer and go, well, that book's wrong. No, it's not. It's right. And then down here, just by the way, see this one? It says, write the repeating decimal as a fraction in simplest form. So they're trying to give you a heads up. Some of these are going to reduce. Okay? All right. Now, wait a minute. What about number 23? They got a whole number out in front. What? So take a look, guys. What if they gave me something like this? 5, oh, come on, pen. 5.5555. Well, here's how you handle that. Ignore this guy. Why? Because he's not repeating. He's a whole number. What you're going to do is you're going to pretend he's not there for a second. And you're going to go, oh, I'll just do the conversion of this, and then I'll add it to that. So I'll go, oh, it's 5 and, 5/9. That's what they meant. That's what you're going to do. And do you see that you have to do that on problem 23, and you have to do that on problem 24? Now, was the book kind? Did they write answer 23 and 24 in mixed number form for you? They did both. They were so gentle. That is so nice. So nice of them. So here we go. The answer key is not in your book. Please, you don't have to do number 25. But if you cannot read the print, just open your book. There it is, page 439. All right, guys, that was one heck of a unit. I'll see you on the flip side. Enjoy this lesson. Bye.